Welcome to AS Educational Channel. Our today's topic is transformer design. While designing the transformer, you should know the two things, that is voltage rating of the winding and core area of a transformer. Now let us consider this is as a stamping. It is a E-shaped stamping. When number of stampings are punched together, it will form the core. So whenever you will make a core, you will, and you are going to place the winding on this core, so this portion will be, let us say, A, and this portion, this will be, let us say, as a B. These measurements are taken in this video as in inches. So core area will be calculated as A into B, that will be in the square inches. So from the tables you can convert this square inches into square centimeters and all another conversions. Now let us see how to find out the power of a transformer. Power of a transformer will be calculated as 5.6 core area, this is square, whole term square. So if you see 5.6 into core area, for the purpose of understanding, I am taking this core as 3 inch into 3 inch. So I will say this is total 9 square inch as the area of the core. So if I do 5.6 into 9, this whole bracket square, I get the value as 2540 watts as a transformer power. We'll understand transformer designing by this simply tabulated table. So we'll solve one by one parameter. So we know the secondary voltage of a transformer and it is 12 volts. We know the primary voltage of a transformer, it is 220 volts. Now we'll calculate the current of secondary. We know the wattage, we know the cross-sectional area. These are two things are known to us. So I will calculate the secondary current, that is 2540 upon 12, which comes to be 211.66 amperes. So this is my secondary current. Now I will same on the same basis I will calculate the primary current. Primary current will be 2540 upon 220, which comes to be 11.54. But for primary side, we have to consider the efficiency of a transformer at 0.9. So by considering the efficiency 0.9, I get here the value, that is what is 10.39 ampere. So I have tabulated almost these two values. Now I will calculate my turns per volt. When I know the turns per volt, I can calculate the primary turns and secondary turns. So I will calculate the turn per volt. So formula for that is E into 10 raised to 8. Actually per volt means E is 1 upon 4.44 into 5M into F. Now we know that this maximum flux is nothing but a product of Bm into A, that is maximum flux is equal to maximum flux density into area of the core. Now I will substitute this value like this. I will write here E into 10 raised to 8 upon 4.44 into my maximum flux density into area of the core into frequency. Now if I substitute this, I'll get here per turn EMF. So I am writing turns per volt, means my volt will be 1. So I will write here value as 1. So 1 into 10 raised to 8 is 10 raised to 8. I will write here 4.44 into, I will write Bm. I have split this pi as Bm into AC, area of the core. So keep it in the mind, Bm we have to take as 60,000 lines of force per square inch, as we are making all the calculations in inch. So I have to take the value as 60,000 lines of force per square inch into area of core. My area of the core was 9. So let us skip this 9. I'll write here area of the core, and this is frequency, and whose value is 50. So if I make the calculations, I will get here as the term that is equal to 7.5 upon area of the core. So turns for formula for finding the turns per volt is 7.5 upon area of the core, and our area of the core is 9 square inch. So I am putting the value as 9. So here the value which I obtained is 0.83. So my turns per volt is 0.83. Now if I want to calculate the primary turns, then I will have to multiply voltage with turns per volt. So my primary turns will be 220 into 0.83, which comes to be 183. And if I want to calculate the secondary turns, then take 12 as secondary voltage. 12 is secondary voltage, and turns per volt is 0.83, which comes to be equal to 10. So this is the calculation for another two values. So we have completed almost of our work. Now the next step is to calculate the conductor size. So for calculating the conductor size, we have to select the copper of density. Various coppers are available from the current density of 2.3 to 4 ampere per square mm. Now for our convenience, we are taking here copper conductor density as 3 ampere per millimeter square. Now if I want to calculate the conductor size, that means conductor area, then what I have to do? I have to divide this current by current density. So this will give you the value of the conductor size, conductor area, because this is in ampere and this is in ampere per mm square. So you will get here the value as a mm square. If you calculate this value, you will get here as a 3.46 millimeter square, and if you calculate this value, you will get here as a 70.56 mm square. See now, from the beginning we have calculated this value. Our calculation for area of the conductor is 3.46, and our calculation for primary and for secondary we have calculated as 70.56 square mm. From the link given below the description, you will find the conductor sizes which are needed, which are actually to be selected for the winding. Now this is our calculation. Now we have to see that link. So what is our basic requirement? Our basic requirement is that we need a primary conductor which can sustain a current of 10.39 ampere and whose at least area should be 3.46 square mm. If you see in the table, you will find the 13 standard wire gauge, 13 SWG is the wire gauge which is suitable, which can carry 10.5 ampere, which is more than our rating, and it is okay. So 10.5 ampere, and its area is 4.22 square mm. So this conductor will be selected for the primary side. For the secondary side, we have to select a conductor in such a way that whose current carrying capacity is more than 211.66 ampere and whose at least area should be 70.56 square mm. We have to select the optimum conductor, so that if you see the table, you will find that there is 4-knot SWG gauge, so not SWG gauge wire, which can carry a current of 227 ampere with the cross-sectional area of 81.07 square mm. So this wire will be selected for the secondary winding. One another thing, in this way we can calculate all the parameters which are required for the transformer design. In short, first we should know the transformer's primary and secondary voltage ratings. Then we can calculate the power of a transformer. How power of a transformer can be calculated? It is 5.6 into Ca whole bracket square. So accordingly we have calculated the power of a transformer. Then later on we have calculated the currents. If we know the power, we can calculate the currents. Then we have derived the formula for turns per volt, and turns per volt is 7.5 upon area of the core. When area of the core is mentioned in square inches, then we have got the turns per volt. This is the formula. So how many turns are required for primary winding? That is voltage of winding into turns per volt. This will give you the number of turns we have calculated for primary and secondary. Same on the same basis we have calculated the conductor size. Conductor size, our primary current was 10.39. We have taken the conductor of copper density, conductor of current carrying density 3 ampere per millimeter square. So accordingly we have calculated the area of the conductors, and later on in the next phase we have gone through the table which is given in the description box, whose link is given on the in the description box, and we have selected the conductor sizes. One another thing I would like to tell you, that if you know the secondary voltage and if you know the secondary current, you can calculate the area of core of a transformer. So this is one formula for calculating the area of core. So 1.152 into root of VSIS. For back tally, we can say area of core in our case. So 1.152 into, if you say secondary voltage, our secondary voltage was 12 volt. Our secondary current was 211.66, and if I calculate this value, of course we are going to get it in terms of square centimeter. This value comes to be equal to 57.96 square centimeter, and if you want to convert it in terms of square inches, 7.90 sorry 8.98 square inch, which is our exactly 9 square inch was our area of the core. In this way we can design the transformer. Thank you for watching this video.